what I'm going to try to cover here is the things that are actually really, really important about bicycle tubes, whether they're in all metals, whether they're tie or aluminum or steel. Tubing measurements, I'm going to talk, this talks about wall thickness, straightness, concentricity, and then something about some strength and hardness numbers. The reason that stuff is important is when guys weld or braze material, if it's not even under stress, wherever the area is that's not even is probably the area that is susceptible to failure. So whether you know, what we do is we're really picky at NOVA about wall thicknesses. We check stuff like at 6 places on the circumference of a tube to make sure it's the same. And if it's not, we have a lot to say to manufacturers. So things like that. Straightness is more of a practical thing that as a builder, you know, you got to put the stuff in a jig, you got to be able to miter it, you got to know that, you know, when you're putting a frame together where you start at one side and you expect it to be in your fixture at another side, it's going to end up there. So when tubes have a lot of bow in them, or even some of the tubes, they get straightened and they get the bow out, but they're a little bit like this, a little bit like a snake. So it's how much of that is tolerable, and so we try to make sure that there's as little of that as is possible with modern manufacturing. Published tensile strengths. Let's go down to that section because that's kind of important. One of the things that you got to kind of know about at least most steels is that there are kind of 2 or 3 different states that steels exist in. One is a fully annealed condition, and that's where you heat it up and you let it soak, and then you very, very slowly cool it. And what that does at a crystalline level is it aligns all the grain structure, makes it very even. It also makes it so that because all of those grain structures are very even, when you start to bend it, wherever those crystalline structures, and you can look this up in the books if you want, most steels are either face-centered cubic or body-centered cubic. In a drawing, you'll see it later in the syllabus, you'll see a C&H sugar cube box. Well, if you were to look at steel at a micro level, that's what you would see. When you start to move it or form it or bend it, if you've got nice even planes that stuff can slide along where the bonds are, it's easier to move it. Some of the other alloys are more complicated. Titanium, for instance, it's hexagonal, so you can imagine stacking a bunch of hexes together and trying to move them very quickly. They sort of end up in a train wreck, and they don't want to move. That's sort of the simple version of work hardening. So let's talk a little bit about the tensile nomenclature. Stress is the measure of force per unit within a body. It's the internal distribution of force. The strain is how the material behaves. So for instance, if you had a piece of steel that's shaped like a tongue depressor, you know, like a wooden popsicle stick, and you put a weight on the end of it, the weight is the stress, and the strain is how much it begins to move. And that's actually what these drawings are about. And this is just kind of trying to give you an idea of what happens to steels as you go from annealed to, which is super soft, to really, really hard, what the behaviors are like. And then I kind of want to make the point that there are some optimal places for materials where they are at a certain hardness, and that certain hardness gives them the maximum amount of strength in the event of a failure. So they resist failure at the highest level that they possibly can. So stress, strain, yield. Yield strength is the total. It's the way out here after it's done everything that it possibly can do to take energy when it goes to here, and then it finally absolutely fails. That's yield. Yield is where a material will not bend back to its original shape. So for instance, if you have a coil spring, you can push on it and you can pull on it, and it will always return. If you take like a little ballpoint pen spring and you pull it out to the point where it it's put permanently stretched, you have caused what I would call a yield in that little spring. It's the same thing in all metals. Basically, at some point, we've all seen this where you take a piece of metal and you bend it, and it hardens, and it hardens, and then it finally breaks. Well, the first time you bent it to where it didn't come back, that was a yield. Fracture toughness is about when a crack initiates, it has a lot to do with how uniform at the microcrystalline level a material is. If it's more uniform and if the grain size is small, well, okay, it behaves like a Kevlar vest. If you had a Kevlar vest and that you had to wear and someone was going to shoot at you, most people would agree that they'd want a really fine weave in their Kevlar, and they'd want lots of it, lots of layers, so that that bullet would not tend to want to pierce through those layers. Instead, if you had a much coarser weave so that the Kevlar could find a hole and start to move through it, well, that's what happens when grain size is large on steels. They tend to, wherever they start a fracture, they just tend to keep going. So you want really fine-grained materials in steels that you use. For that matter, aluminum's also, you want really fine grain, and you want alloys that when you weld them, when they recrystallize, you want them not to form really big grains. You want them to form grains, again, that are as small as possible because they will resist. Toughness. Toughness is also sort of related to this area underneath this curve. It's not this, but it's related. Toughness is about, well, for instance, any guys here with auto racing experience, connecting rods, that kind of stuff? Okay. If you take a stock rod, usually they will stretch because they're not very good. They might do a little stretch and then they're going to fail. The best rods usually, at least if they're in steel, are rods where they've been slightly hardened so that they will stay in their same shape under a lot of harsh use. And then if they do fail, you want them to bend slightly. You don't want them to ever come apart. So it's kind of the same story. That's where fracture toughness, that's where toughness in general is an issue. And toughness is the single biggest determinant when a material is going to fail, on how it's going to fail. Okay, let's get to the meat of things, and this is kind of a stress strain curve, and I'll explain what this really means in terms of the metal. If you took like a piece of a steel tube or an aluminum tube and you stuck it in a tester and you started to pull it apart, at first when you were pulling it, if it was a solid and you put a dial indicator on it, you'd see it, it do what all humans do when they're put on the rack. So this is, if you put your steel on the Iron Maiden, the stretcher, and you measured your waistline as you're getting stretched, your waistline would start getting skinnier as you get pulled more. Well, that's what happens with steels. Again, if it's within what is called a proportionate limit, where it's still in its springy area, if you took the pressure off, it would come back. At the point where the waist begins to narrow of the dimension that you're stretching, and it becomes permanent, that's the point of what is referred to as yield. And yield in engineering terms is always, if you put stress and then you start to measure, well, how much is it changing? Yield is always the place where this slope, and this slope of this stress strain is always going to be a straight line. It's just a proportion. At the point where it deviates 0.2% from this graph is where most engineers would define the yield point. Now, in this case, I just did some kind of crazy illustrations of what you can do with just straight up chromoly. Everybody knows chromoly. It's everywhere. And the idea of this was to tell you something about how you can optimize, let's say, this is just kind of a case study of chromoly. If you were to heat chromoly to where it's really, really hard, and this is what is called a Rockwell hardness. It's something it's a common measurement in industry for hardness of any number of materials. But for steels, most steels are in what is referred to as a C range. So in this case, let's say that you took a chromoly sample and you heated it to where it's hard. If you were to talk about the tensile numbers, the numbers that everybody quotes in their bicycle tubing things or in their aluminum tubing things for that matter, this would equate to somewhere around 140,000 pounds per square inch of strength, maybe a little more than that. That's pretty hard for chromoly. In fact, it's probably more than that. Well, if you were to stretch that, it would go, and then it would just go snap. It wouldn't have much of a stretch before it failed. It would just go, and then stop. Well, the total energy underneath this graph, this area, is really the determining factor. The fact that it had a tensile strength of 145 to 150, which is what manufacturers will talk about, can be misleading because the material wasn't actually able to absorb that much energy. And this is the big secret. If you take that same chromoly and you put it in its fully annealed state, which is actually, it's not even 20, it's probably more like 18, which is almost immeasurable, then the material, when it fails, it just keeps stretching like taffy. And so it'll stretch, and it finally will fail. Well, that's more like this. If this started to fail here, and it just goes like taffy, and at some point it starts to work hard a little bit, and then whoop, that's it. Then you plot this area. So you're comparing this area to this area. Well, the truth is this graph probably needs to be a little bit lower, but what I want to show here is that neither one of these are optimal. They're both less than the material could be. So what you want to do in making tubes for bicycles, because of the geometry of bikes and how they're welded, is you want to find a way to make a material that will fail a little bit higher, but still have some of this. This distance is the ductility of the material. So what you're trying to do is you're trying to optimize this so that whatever this area is the highest. And that's the optimal way of making tubing for bicycles. As it turns out, you'll never see this stuff published because the makers don't talk about it. We published a study at Lehigh University where we did find this out, and we tested samples from a bunch of different makers. I'll get into that in a few moments. I want to talk a little bit about work hardening and heat treating and how they're kind of similar. It's just a different way of getting to a similar result. When you work harden material, as you are pushing those sugar cubes, as they get to where they don't align really well and they start to block each other, those bonds start to go into compression in some places and in tension in others. So those bonds have stored energy. That's where the additional strength comes from, with whether it's a cold worked aluminum or a cold worked steel. It doesn't matter. If you roll it enough, you can do some grain refinement, but actually work harden it as well. If you draw it the way we make butted tubes for frames, that work hardens it too. When you heat treat, it does a similar thing, but it's not exactly the same. What happens is when you heat the material up, those bonds, those crystalline bonds that are holding this stuff together, start to excite, they start to vibrate. And then, if you cool that material really quickly, then some of those bonds are in a stretch state like the spring that's been pulled out. Some of them are in the spring state where it's been compressed. Some of them are in neutral state. So you're storing energy in those bonds. You're just doing it a different way. And sometimes the heat treating way is better. Sometimes the cold working way is better. Sometimes a combination of both is the best. So what we're looking for here to get this, for instance, in a bicycle tube, which is very, if you think about it, it's pretty well evolved, is normally you're going to cold work a tube, and that's going to give you a certain amount of additional hardness, let's say in here somewhere, and then you're going to try to do, let's say, a mild heat treatment, and that's probably, for instance, in chromoly, going to give you the optimal result. Depending on the alloy, some of the alloys are harder to begin with, and you don't have to do as much with them. In fact, you're better off if you don't. They'll actually be more tough, there's that word again, if they're not heat treated. Okay, so go to page 5, I think it's page 5. It shows the engineering diagram with the different 4130, 4140, 4150. And this is just a quick illustration of what happens when you add carbon to an existing alloy. The only thing that's changing when you see these curves, these stress strain curves, is the amount of carbon that's in the alloy. And as you increase the carbon, it increases the hardness. But as you see, those lines stop sooner. The 4150 stops sooner than the 4130 does. And you can pretty much see that if you were going to have to plot the areas again, the 4131 would have the most area underneath. So it would in fact be the toughness king. So let's roll on to the next illustration. This is a picture of my dad, who was a race car fabricator, testing with a lab-grade hardness tester that we use. One of the things that we sort of discovered is that all of the manufacturers have, they have their published values in their tubing. They'll tell you what the strength is. But that strength actually can vary with things like, well, is it where it was butted, where it got less work hardening, or is it in the thin section where they really work hardened it? The tube can actually have differing hardness even within the tube because of the way it was processed. So we, being who we are, wanted to know without ambiguity what the real hardnesses of materials were, not what a manufacturer would say, for any number of reasons, diagnostic reasons, as well as just having a confidence in what we're selling. So for us, we have the ability to take any tube. You see these rings. These are cutoffs of tubes where we cut them wet so that there's no thermal thing going on with them. We deburr them, and then we use a lab-grade hardness tester to get a Rockwell measurement. You can go to almost any engineering handbook. You can correlate a Rockwell hardness to a tensile number. Machinery's handbook has a little bit of that stuff. The metals handbook, which is a book about so big, that book has table after table after table of this stuff. So it's very easy to understand by looking at a hardness check what the tensile numbers, what the strength that a manufacturer would say that material would have is. So we go through that on a routine basis. Is what happens when you weld a tube. And we hear a lot about air hardening, and the companies that talk about an air hardening steel that they use in their tubing, they are indeed air hardening materials, but the phrase without context is a little bit misleading, and I'll show you why when you look at this graph. Virtually all materials in bicycle frames, because the wall thicknesses are thin relative to the geometry of the tubes, all of those materials are air hardened. It's because they cool rapidly. So in this graph, where you see on the left side these two different materials, that was what the material started as before it was welded. And then as you move towards where it's called an inductor center, the inductor center was essentially where the TIG weld started. So if you can visualize what's happening is, where it says inductor center, think of that as being the backside of a head tube. And then this graph is the hardness of that top tube as it's moving away from that head tube. So what's happening is you'll see that it goes up, it gets quite a bit harder, and then it drops, and then these graphs don't actually show it, but it actually returns to the starting point of what it initially was. So what you can see with this graph, though, that's instructive, is that all the materials, when you weld them, both get harder and they get softer. So there's a spot where they get softer, and the first thought that you know, if you're an engineering guy, you're going to think is, oh, okay, that's where it's going to fail because it's going to be weaker. You know, it doesn't turn out that way, but we'll talk about that in a minute or so. So what this is trying to show you is when you TIG or abrase, the material hardness, everybody knows about a heat affected zone, and that's really what this is showing. Where you see that the lowest point where it's soft and where it starts to return, if you saw the blue lines on the TIG joint, that's about where those blue lines would appear. So that's kind of just a background on what we did. This is where we put together the different kind of definitions that we've talked about. We wanted to see something about the hardness of materials, and we wanted to see something about what happens when you weld them and when you pull them apart as a way of modeling what happens in a failure, like a crash. It's the inverse, but it's doing the same thing. So what we did was we had major manufacturers' tubes. We had a sample of 3 of each that we had a famous guy, CSIP Design, he's here in the show, Jeremy at CSIP, and his brother at the time, who was out, Chris King. We had them mitered, each manufacturer's tube, same diameter, same wall thickness, miter them at 90 degrees to a head tube, TIG them all at the same time, same E70 S3 rod, I believe. That's what they used on them. And then we got them back from them, we blind labeled them so no one would know what they were. We sent them off to Lehigh University, and we commissioned a test with a guy named Dr. Delph, Professor Terry Delph at Lehigh. And what we did is we pulled these apart, we put some instruments on, some strain gauges, and we started out by saying, okay, we think these tubes are going to fail, going back to that graph that we were looking at the bottom of the well in that drawing, because that's the weakest point. That was our idea, and we can, yeah, these were assumptions. If you go halfway down the page, it'll say assumptions of what would happen in heat-affected zones. The weakest spot that should fail is the heat-affected zone because the strength is the lowest. That's what we thought. And the material with the highest published tensile strengths should be strongest. Well, I've kind of given you a preview that the highest is not necessarily the best in failure. So what actually happened with that is that the materials that had a specific ductility, remember I was talking about optimizing. Well, the materials that had the best ductility have kind of what I think of as a holy grail number. Again, none of the manufacturers tell you this stuff. We just learned it by doing a university test. The holy grail number for ductility as measured by elongation is 12 to 13%. What does that mean? What that means is that the material will change its dimensions by 12 to 13% before it fully fails. That's how much stretch and tear the material needs to have. Some of the materials that you see in our industry are very much like this. They are very, very hard, and they go, 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 and they snap. And that's actually what we saw in this test. Without talking about names and so forth, we did the 4 major manufacturers at that time, and the 2 that had the highest tensile strengths were the ones that failed first. The interesting thing about the failures with TIG welds is that when you have a TIG weld, and I'll just kind of show you what I mean. Say this is the back of a head tube. Here's a top tube that's joining. Let's see if I can do this. And then here's a weld. TIG welds always have little pinpoint stresses. You can't see them, but they're there. There will be a little pinpoint stress. It's like a dot, and this is what we could see on the stress strain data. And what will happen is that will hold on, hold on, hold on, and then at some point it will release. And if the material has ductility, it will cold work. It'll slightly release and then it'll go to another spot. It'll do that same thing where that stress strain is at a micro level is real, real high. It will actually crystallinely move, and it will give that strength up. If the material has ductility, it will literally do this thousands of times before it fails. So it'll do this little micro-deform, spread the stress out, goes to the next highest area where, again, that pinpoint stress is really, really high. It'll micro-deform, move on to the next one. So this is the mechanism of failure in tubes, without a doubt. So if the tube is really hard, though, this is the secret. When the tubes that have the bigger numbers are here, and whenever you find the first stress strain point, it will hold on, hold on, hold on, hold on, hold on, and snap. Just like that. Hold on, hold on, hold on, and snap. What you want is you want this number so that it will do this idea of moving around the tube and at a micro level dispersing those stresses over and over and over. And what we found in our test was that the materials that were here, that were the better alloys, in our testing seemed to be materials that had values of between 150 to about 160 with the higher strength alloys. When you got up past that, your area under the curve started going down. The total energy that it took to fail that tube started to reduce. So this was kind of the secret. The other kind of odd secret that we discovered was that where we thought the heat affected zones were out here, let's say, where you see your blue lines, you know, when you weld them, none of the tubes fail. Why is that? It's because of geometry. It has nothing to do with the material. It has to do with the idea that where these tubes are joined is where the stresses are the highest, right on the edges of those welds. By the time you get back to where you would see your typical heat-affected zone lines where you join a tube, so-called HAZ, I don't know if you can see that. I'll see if I can write it to where it can be seen. Heat-affected zone. Out here where the heat-affected zone is, by the time you get out that far away from the tube, and it's not very far, the stresses are very evenly distributed around the radius of the tube. It's a radial distribution. The tubes do not fail here, even though they're softer. They just don't. They fail here. So the idea there is that there are some specific things that you want tubes to do. The other things that we found out that have to do with process, and this actually has to do with why you should buy from certain tube makers versus others. Some people have really good process control, and others don't have really good process control. With that in mind, you need really good process control so that when you test these, and what we did is we tested these and we wanted to see that if they were going to fail, we wanted them all to fail within a very narrow range. If the range was wide on failure, that meant that the people that were making the tubing did not have good control of the process, whether it was in a heat treatment phase or in a draw step, you know, if they didn't use clean material. The best way of looking at the final outcome when you do a test like this is you look for standards of deviation. And we were looking for really tight standards of deviation. Some manufacturers, actually the ones we represent, had the tightest standards of deviation. The others, most of them were pretty good. There were some that had very wide standards of deviation, which to us, even though their values might have been pretty good on an average, but if they had a lot of standard deviation, that meant one tube was substantially different from another. And so we wanted to make sure that we didn't have that kind of process variation when we were buying tubing. Here's the conclusion, last page. Tensile and hardness really do matter. And it's not just one or the other, it's really the balance of both of those. Not enough, a frame prematurely fails, it acts like taffy, it just stretches and bends. Too much, and it literally separates at the joint. And if you've been around very many frames where guys went to really thin, super hard tubes and you watch them TIG them, you'll have seen some that had cracks right around the edges of the welds. Just too hard. Ductility and elongation matters. There are optimal numbers in elongation, these numbers, that give the best compromise, the best balance, so that you're getting the best strength. This. Not this, not this, this. This has the largest area. The ideal behavior is for a material to go as far as possible in its elastic area, to go as far as you can, and then have enough elongation to fail gracefully, so that you don't have a liability issue, and you also don't have a customer that's pissed because his bike bent when it probably really shouldn't have. These numbers are from empirical observations, and there's my conclusion, there's my 12 to 13%. If the processing is really, really good with the tubing, and they can hold that number, it doesn't matter what the alloy is. If they hit this number with what is delivered to a frame builder, they've delivered what is the best for whatever alloy they've picked. So this is really where the industry needs to go, but again, this is kind of the numbers that no one's going to talk about. So these are the internal numbers of what the tubes need to be when they're delivered to a frame builder to give the best compromises of strength and weight and reliability. Any questions?